So now we move forward in time a little bit. Thompson's experiment. Thompson took a device which launches something called alpha particles, and he fired them at defenseless atoms, specifically of gold, which are huge atoms. Probably should just go ahead and make them huge. Why not do it right? Make them huge. And what he discovered was sheer boredom. The vast majority of alpha particles went through the back and slammed into his little feet. Had a little photo tube in back, a little phosphorescent tube. An electron strikes that, or a charged particle of any sort strikes it. As it slows down inside, it emits a light. And so, by firing alpha particles, where you put the gold in there, the gold, very thin gold sheet. By the way, we now know it's about 10 atoms thick. At the time, he had no idea. That's not true, but he had less idea. So 10 atoms thick, so I had to get through 10 of these atoms before it went through. And basically, almost, it was just like shooting thin air. There was nothing there. And from this, he was struggling because he knew you could rub off electrical charge. And he knew that these electrical charges did, because of another experiment he did know these electrical charges could be scraped off in chunks. And yet, only occasionally he'd hit them. Now, occasionally he'd hit one of these electrons. These electrons would be deflected outwards, and it would strike the tube. And because of the way he set it up, it would actually set up a slightly different color. So he knew that when he got an electron versus when he got an alpha particle, and because of that, he knew what was going on. He knew that occasionally an electron, and most times he's hitting nothing. And so he came up with what was called the Plum pudding model. He believed atoms were basically a big thing of goo with little nuggets, plums as it were. These plums were the negative charges. And that if you struck it just right and happened to hit one of these negative charges, it would pop out. But for the most part, you passed right through. It's like shooting bullets at Play-Doh, at pudding. The bullet's going to pass through every single time. Fair enough? Fair enough. Along comes a guy named Rutherford. And Rutherford does the exact same experiment. Now, he's given credit for the exact same experiment. There is abundant evidence that it was one of his lab assistants that did this, but we'll give him credit because he's the one who figured out what it meant, which is kind of more important than what it was. He had the gold foil in front. He had the same lab as before. He had a tube in the back, and he was firing alpha particles. And again, they were trying to figure out how likely you were to hit. Once you got a cool invention like this, you keep using it. Well, for reasons that are historically not completely understood, a fluorescent tube got put here. It's suspected that one of his lab assistants has put it here, and sat there all day in a dark closet. This was his job. You sit in a dark closet. You have this device that shoots alpha particles every so often. You look for lights. Well, this is a pretty boring experiment because, as Thompson pointed out, every single one of these went here. Except they don't. Every so often, when these extraordinarily high-speed particles, which is almost the same mass as an atom, hits an atom and bounces off and lights this tube. Well, there's no explanation for that. Almost no explanation. It would only way it could possibly happen is if the whole atom had no mass at all, or virtually no mass at all, except for these electrons on the outside that are very low mass, except for all the mass inside the atoms in a very small spot. Equivalent, if I was standing in my classroom in Incline Village, my first layer of electrons would have to be all the way out just on the other side of Reno. Okay? So most of an atom would have to be dead space. And so he repeated the experiment over and over again until he believed it, that in fact atoms were mostly dead space, a very small, incredibly dense nucleus, and then little tiny electrons whipping around the outside, minding their own business. Okay? All right, so this is the Rutherford experiment and the Rutherford model. Rutherford comes up with this idea of electrons on the outside and almost all the charge in the middle in a solid chunk. Okay? Now, chemistry spent some more time. They hopefully talked about shells and things. I'm not going to do that. Instead, what I'm going to do is I'm going to move on to why this affects physics. Why it affects physics is when you scrape off, when you have two things that you rub together. Again, we deal with big things typically. If I take a cloth and I'm rubbing it on a stick, what happens is the stick will pick up, and we'll just say a negative charge. Again, you can measure which kind by measuring against other things that you know are positive or negative, which means the electrons jumped across here and leave behind an abundance of positive charges. Okay? This is called, so then when I take this negatively charged thing, hopefully metallic, and I put it against another metallic object, the electrons, when I tap them together, the electrons can jump across, and we call this conduction, meaning that both sides now have charge. Not all of it jumps off. That never happens. But some of it jumps off. Why? Why are they doing this to begin with? Well, electrons don't like each other. Remember, they're repelled. And so if you have a great big pile of electrons here, you can see why some of them want to get off in the part that has none, or actually has equal amounts of positive and negative. And then they'll keep doing that until the electrons are equally spaced in both sides, and they go, you know what? That's it. No more jumping across. All right? So moving forward, there are some things that allow the flow of charge and some things that don't. So for example, if I take my negative thing and I push it up against a balloon, say, and we're going to use balloons a lot in the near future. If I take my rubber rod or something that I put extra charges on, well, when I tap the two together, only that electron which can jump directly on the balloon does anything. The rest of it does what? Stays on my rubber rod. Because they can't spread out in the balloon and they can't move around in the rubber rod, only one small area would be charged. Because this is not a conductor, this is an insulator. Okay? So things like rubber, we wrap wires with essentially rubber because we don't want to grab one wire, grab another wire, and get fried. Okay? So hopefully somewhere inside of your box you have wires that are coated in it's more plastic than rubber, but let's just say rubber for our purposes. And so the charges cannot move from one wire to the other wire, which keeps your house from burning down. On the other hand, if you're one of these crazy people that keeps pulling on your wires, you could rub off the insulation, rub the insulation on the wire next to it, and then electrons will happily travel to this other wire, which happens to be the other charge at that moment. If you have anything flammable between the two, your house burns down. Okay? So be nice to your insulation. Now, that's not what happened initially with our pith ball. With our pith ball, what we had here is we had our comb, which was negatively charged. We brought it close to the pith ball. The pith ball has negative, plus, plus, minus. This negative right here says, oh, dear Lord, I'm really close to these negatives. I'm repelled by that awful thought, and so I'm going to move over here. Meaning your pith ball eventually looks like plus, plus, with your negatives revealed on the other side. And so, as such, this positives are closer to the negative, and the negatives are farther away. So the plus negative force is stronger, so I'm attracted, and the pith ball wants to get close to your comb. And so we call this charged by induction. This thing's not actually charged, but it's acting like it's charged because the like charge is being repelled the other way. Okay? By the way, the same thing happens if I have a positive charge. I have a positive charge rod, and I have a pith ball. The negatives would be attracted to it, so the negatives end up on this side, and the positives end up over here, the revealed positive on this side, and it'd still be attracted, right? So again, you understand why they didn't know which one was moving, because you did the same exact experiment, you get the same exact results, you have no idea which one's moving where, right? So therefore, induction is, again, this idea where you have something that's neutral, or could be neutral, doesn't have to be neutral necessarily, but let's call it neutral, where the charges move around, so they act like they're charged even though they're not. And by the way, if I move this away, it's not charged anymore. It goes back to where it was. Electrons flow back to where they were. Okay? So that's called induction. Now, party trick. Hopefully you have a balloon in your house, right? You should know by now if you have a wall, your walls have plus or minus charges. Don't choose something that's conductive because it won't work. But if you have something that's mostly an insulator, can't be a complete insulator, won't work either, and you take a balloon, and we rub it against your hair. First of all, you'll know this works if your hair starts sticking up, which means you've got negative charge. Rub one side in particular. You want to rub it a lot, and so you got one side of the balloon that's negative, and bring it close to the wall. What happens is as follows. The electrons go, ah, we hate this, we're out of here, and so your wall ends up looking like this, plus, 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 minus, 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 and your balloon, as it gets closer and closer, ends up attracted to it. And in fact, a couple electrons will jump across, which makes the wall net negative. But those electrons will also flee. And because your balloon is not a conductor, what happens is your balloon, where it's touching the wall, has no charge. These remain negative over here, right? And so as these are negative, and the wall is, part that's touching the wall is gone, is now neutral, the positives that are attracted to it and the negatives that are repelled are back here, so the balloon sticks to the wall. So you should do this. If you've never done this before, you should absolutely take a balloon from your household supplies, blow it up, tie a knot in it, rub your head, take the balloon, stick it to a normal wall. If it doesn't work, rub it some more. It will eventually stick to the wall. And yes, you don't need tape to stick balloons to the wall. All right. Unfortunately, I now have to do another experiment. So here's what we're going to do. We're going to pause this, and then I'm going to show you another device called an electroscope. I'm going to use my ghetto Walmart version, but hopefully we'll be able to understand what's going on, and I'll be able to give you some work to do so I can stop talking, because as you know, me talking is a dread and a drear.